Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is work and energy. We're actually going to be tackling two sections in the textbook today, which in the homework schedule are listed as two separate lessons, but we're going to combine them because you really can't talk about one without the other. Like I said, the topic is work and energy, and you've probably heard the term energy before. I know you've discussed it throughout your science career, but the concept of work might be something that's new to you. You might think you know what work is, and you may have a very good, accurate idea of what it is, but in physics it has a very specific definition, which of course is related to energy, and today we're going to find out what that relationship is. So in a moment I'll ask you to pause the video, have a look at the exact questions that we're going to be answering, as well as having a look at where we are in the homework schedule, and also what the learning goals and success criteria are. So please do that now. Okay, and you're back, and we're going to dive right into things. First off, just a quick discussion, hopefully a refresher to many of you, on some of the different types of energy. Before we talk about what energy actually is in terms of one simple definition or one single definition, let's look at the different forms of energy that we have become familiar with as we've studied science over the years. Some of them are listed here, and I'm sure you're going to recognize some of them. For example, elastic energy. I'm sure you've stretched an elastic band, or maybe a spring, or maybe you've compressed a spring at some point. We call the energy that gets stored in a spring when you compress it and then let it sort of rebound, or when you stretch it and let it snap back. We call that elastic energy. Let's have a look at gravitational energy. Anytime you lift something up off the ground and then drop it, we notice that some energy has materialized in some way. Where did this energy come from? Well, we say that because an object has been lifted above the ground, it has something called gravitational energy. It has the ability that if we let go of it, it will start moving. A good example of this might be dropping a rock onto a maybe a metal peg that you use when you go camping and you want to secure your tent in the ground. We use the Earth's gravity to help us drive that peg into the ground. There's a sort of energy in there. We call it gravitational energy. Let's look at another one that we're all familiar with. This video is being recorded in the middle of winter right now, and it's very cold outside. A lot of our homes are directly using a chemical, probably natural gas, to burn and create heat, which can be circulated through the home to keep us warm. So the chemicals that we burn have a certain energy within them, and we call this chemical energy. Of course, as I'm recording this, I'm using the electricity that's being supplied to my home. Some of this electricity, no doubt, is being produced at one of Ontario's nuclear power generating stations. And if you aren't familiar with nuclear power, well, let's just say right now that within the nucleus of an atom, there are particles we're all familiar with called protons, and these protons, having the same electrical charge, they want to, or they are repelling one another. However, something is holding them together. After all, they are existing within the tiny confines of the nucleus. And so what is holding them together? Well, as you know from a previous video, that force is called the strong nuclear force, but it's got to overcome that repulsion that we learned about a long time ago when you learned the phrase, like charges repel. That means there's some sort of energy stored up within the nucleus because those protons, they don't want to be so close together. Well, that energy can be released and it can be harnessed to produce electricity. We call that nuclear energy. And of course, a much more dramatic example of this nuclear energy would be nuclear bombs that we've all heard about. Looking at some other forms of energy, there's kinetic energy, the kind of energy associated with movement. For example, if someone throws a ball at you and it hits you, you feel some pain. Some energy has been transferred to you from that ball. The ball had kinetic energy by virtue of the fact that it was moving. Let's look at another kind of energy that deals with movement, this one called thermal energy, the kind of movement that's associated with the particles in a substance. You've learned that the hotter a substance is, that corresponds to faster movement of the particles within it. We call this thermal energy. How about sound energy, something we studied a lot earlier in the course? The energy associated with the vibration of particles within a medium, let's say air as an example, carrying vibrational energy from one point to another, maybe from my throat, my voice, to your ears. Let's look at another kind of energy associated with movement, electromagnetic. Perhaps the light that's coming to us from the sun, traveling through space and bringing us all the energy that plants need to undergo photosynthesis and to produce food for us. One kind of energy that you may not have heard of, called rest mass energy, this is the energy that is made famous by Einstein's equation E equals mc squared. This formula says that energy is equal to mass times c, which is the speed of light, squared, which tells you that mass and energy have some sort of relation. Well, as it turns out, any object, just by virtue of the fact that it's sitting there and has a certain mass, therefore, if we plug that mass into this equation, we get a certain energy. And this is a really interesting equation because, as you'll see if you go on to study physics, there's some really amazing things that happen deep within the nucleus of many atoms. What can happen in this case is the atom can actually transform some of its mass into action. Of course, the reverse can happen as well. Energy can be transformed into matter. There's a really neat process in nature called pair production, as in not the fruit a pear, but a pair of particles gets produced. So if you want to look this up, it's called pair production. A pair of particles can be produced. Particles that we normally think of as matter, they're produced from energy that we normally think of as light or electromagnetic energy. It's very, very cool, and if you're interested in particle physics, you should definitely look this up. Anyway, many, many different types of energy, and of course, when we're talking about energy, as with anything else in physics, we have to be able to measure it. So how do we measure energy? Well, the SI unit, or the metric unit for energy, is of course the joule. You would have learned about this back probably in grade 9, and I'm sure you've heard it many times since. Joule is the basic unit of measurement for energy, but it's not the only one. If you look on any of the food packages that you get whenever you buy, let's say, a chocolate bar, you'll see this, calories, and this is often used when discussing food energy. It's also the unit of measurement of energy that the Americans use in the imperial system. And what other units are there? Well, you may come across this strange sounding unit, an erg. This is actually used by certain scientists, not used too much anymore. It's used by astronomers and sometimes particle physicists. And another one that you'll see, and this is one you don't want to see because this is the one you get when you're a homeowner and you get your electricity bill. It's called a kilowatt hour. Not a kilowatt per hour, but a kilowatt hour. And we will learn more about this later in the unit, but when I get my electricity bill every couple of months and I have to pay however many hundreds of dollars, they tell me how many kilowatt hours of energy I've used in my home, and that's because it's a much more convenient unit of energy than the joule, as we will see. So anyway, there's a basic introduction to different kinds of energy and how we measure them. Now we're going to go and look at some of the characteristics of energy. One of the main characteristics of energy, and one of the most important, is that energy can change form. What do I mean when I say energy can change form? Well, think about a wind turbine, and to help you to visualize this, I've got a YouTube video set up for you. This one I found is kind of neat. It looks like someone got into a helicopter and took a ride through a wind farm, and I've muted the sound. I'm just going to play it and sort of do my own narration. You can see that they are flying up toward a wind turbine and are now hovering. You see that the wind is blowing the turbine is spinning, there's many others in the distance. And what is going on here? Well, this is happening all around the world more and more as we try to get away from burning fossil fuels that cause pollution to our air, and we try to get to so-called cleaner, renewable forms of energy. What's happening here? Well, you certainly saw that the wind turbine was moving. And so if we go back to our list of energies here, which of these energies is the energy of movement? If you guessed that it was kinetic, you are right. Kinetic energy is the energy of movement. So we know here that the wind turbine has kinetic energy. Now, where did it get that kinetic energy from? You can probably guess that the wind was pushing on it. So the kinetic energy of the turbine comes to us courtesy of the kinetic energy of the wind. The wind does the pushing, and the turbine ends up turning. And this, of course, for us produces electricity. And of course, you may use the electricity in your home to maybe put on a light so that you can see what you're doing. Of course, the light bulbs that we often use have an unfortunate side effect. They're not very efficient at producing light. In addition to light, they produce a whole lot of heat. You get a feel for this anytime you try to change a light bulb that just burned out. So what do we see so far? We see kinetic energy changing into electrical energy, which is changed into light and heat. We can go backward through this chain. Where did the wind get its energy from? This, of course, if you study weather, you know that this comes from the uneven heating of the Earth's atmosphere. Different land masses heat up differently when they're hit by sunlight for different amounts of time and with different intensities. So really, ultimately, the sun is responsible for driving the wind, which turns the turbine, which produces the electricity, which produces the light and the heat. And we can go even further back than this. Where does the sun get its energy from? Well, if you study astronomy and stars, you'll know that the sun gets its energy from nuclear fusion. The joining of light atoms, like hydrogen, for example, into heavier ones, helium, which can only occur under very extreme circumstances, such as those found in the core of a star like our sun. So isn't this an amazing chain that we start with tiny, tiny atoms inside a star that's very far away from us, which ultimately leads to wind patterns which turn a turbine, which create electricity, which produce light and heat. And so we get the idea that energy can change form. And if we look back at the list of energies, I bet you can identify some of the ones we've talked about. There's nuclear right there for sure. There would be kinetic, the movement of the turbine; thermal, the motion of the particles in the air; the electromagnetic, the energy coming to us from the sun; and of course, the electromagnetic in terms of turning on your lights, and then the heat that's produced, and so on and so forth. But getting back to the characteristics of energy, not only can it change form, however, in what's called an isolated system, and this means if we look at a system where no matter or energy is allowed to enter or exit, in other words, if we kind of look at a system in isolation, there is a rule in science, and a rule not that we decided was a rule, but a rule based on observations. Scientists have been observing many, many different kinds of systems in nature for centuries now, and they've noticed a peculiar fact. No one has ever noticed a difference to the fact that if you look at the system in isolation, then the total amount of energy is constant, or what scientists call conserved. This is, of course, known as the law of conservation of energy, which I'm sure you've heard of in your studies in the past. By the way, just so you know, the conservation here doesn't mean conservation in the sense that we turn out our lights to conserve energy, or we don't turn on our air conditioner in the summer in order to conserve energy. The conservation here means that the total number of joules of energy is constant. So if we go back to this page and we look at all of the energy transformations that can occur in any process, and if we measure the number of joules or calories or ergs or kilowatt hours all throughout the process, we find that the total number at any given moment is the same. So in the wind turbine example, what I would be saying is if we start with the nuclear reactions occurring in the sun, and we don't let any other energy enter our calculation, then if we follow how much light came to us from the sun, from those very fusion reactions, and then if we look at all of the wind, the energy in the wind, thermal energy in the air that resulted from the heating from the sun, and then we look at all of the kinetic energy from that spinning turbine blade, and so on and so forth, the total amount at all times is constant. And this is a very important physical concept, because if we know that this is a fact and that no one has ever noticed a difference, and therefore we believe that it's true, then that means we can use it to perform calculations. And you're going to see this later on in this unit. But keep that in mind. The law of conservation of energy, very, very important. All right, so now let's look at a concept called work and how it's related to energy. And to get us started on this concept, I want you to have a look at this spring here. This is an image from Google Images, and you can see the spring has kind of been stretched a little bit. Well, I want you to imagine grabbing both ends of the spring and pulling apart. What's going to happen? Well, using your physics knowledge, you know that you are going to exert a force on the spring, and it's going to move a certain distance. It's going to stretch. Well, if you do that, and now you've stretched the spring out, here's what I want you to imagine doing next. I want you to imagine letting go of the spring. What's going to happen? The spring is going to snap back into position. It's suddenly going to gain kinetic energy. And if you believe what I just described as the law of conservation of energy, you know that you can't just get kinetic energy from nowhere. You get it from somewhere. In this example of stretching the spring, that somewhere was from the force that you applied, symbol F, and the distance over which you applied it, symbol delta D. And actually, in physics, we call work the product of force and displacement. So in physics, work is equal to force times, or distance in this case. Since we're going in one direction, the distance and displacement are the same. So let's call it force times distance gives you work. And of course, the more you stretch this, the more force and the more distance, the more, when you release it, it will snap back violently and create or give you kinetic energy. So we know more force, more distance, more work, more energy. Work, as it turns out, is measured in joules. Force, of course, is measured in newtons, and distance is measured in meters. So what we get from this is that 1 joule equals 1 newton times a meter, or a newton meter. Now let's look at some examples of work being done other than just this spring. These images are from your textbook Physics 11 by Addison Wesley in section 4.1. And if we take a look at the first image, we see a person lifting a box. Obviously, this person is exerting force, and of course the person is lifting the box, so there's a displacement. Here we have the same kind of situation as with the spring. Force times distance gives you work. Work is being done. Here someone is pushing a box. In order to push a box, you have to exert a force. And of course, because you're moving it, there's a displacement. Once again, work is being done. But now let's look at some examples where you might think you're doing work because something's happening, but in fact you aren't doing any work. Here someone is holding a box, but as the picture says, there's no motion. So stand somewhere and hold a box for a long period of time. You might get tired, but sorry, no work is being done on that box. One way to think of this is you aren't getting the box moving, so you're not giving it any energy. You're also not lifting it, so you're not raising it higher up. In other words, you're not giving it any of what we call gravitational energy. You see, if you were to lift that box higher up and it gained more gravitational energy because it was higher up, then if it were to fall down, it might convert that gravitational energy into kinetic energy. But because we don't have that situation happening here, because the box isn't moving, no work is being done. Here's an example, a spacecraft traveling through space, but way out in deep space where there's very little or almost no gravity acting on it. And as you can see, it doesn't have its engines turned on, so we can get rid of that little diagram that I just drew. This is just an object coasting through space. If you've been in my class, you've seen something called a soccer disc, which is an object that hovers above the ground using a fan, and we just give it a little kick and it goes hovering along the ground all the way down the hallway unless it bumps into something. There's no friction, it keeps going. Similar idea here, a spacecraft in deep space. You could also think of an air hockey puck on an air hockey table. You give that thing a push, it just keeps going until it hits something. If that's the case, then we know from Newton's first law, what I like to call N1, there's no unbalanced force acting on that object, although there is a displacement. Is there work being done? Well, Newton's first law tells us here that there doesn't have to be a force acting for there to be motion. The object is just coasting along because, like we once heard in the Eureka videos that we watched, things like to keep on doing what they were already doing. You don't have to force them. You don't have to do work. Here, no work is being done. So just because there's motion, or just because it seems like something's happening, doesn't always mean work is being done. Let's take a look at a few more examples. These ones a little bit trickier. Here a person is holding a box, just like the person was over here, only this time the person is on skis and is just gliding along. Is the person doing work? Pause the video for a moment and think about it. Okay, and you're back. The answer is the person is still not doing any work. Definitely the person's not lifting the object, and even though the person is exerting a force and there is a displacement, one thing to note here is that the displacement is in the forward direction, yet the force is in the upward direction. Just try to draw that a little straighter. There we go. The force is in the upward direction, so I'll label those delta D, and here is F. In this case, the force is holding the object up, but it's not lifting it. The displacement is happening because, yeah, the person's moving, but the person is just gliding. Whatever force the person exerted at some point to get moving forward, that force now does not need to be applied. So either way you look at it here, no work is being done. Here's a situation where a person is pulling something, and because of the way that he's pulling it, there's an angle formed between the force and the displacement. How much work gets done here? Well, if you look at what's going on, we've got a force which has a little bit of a part or component going this way, and it's got a little bit of a component going that way. This is the idea of components that we first encountered when we talked about projectile motion. Remember when we talked about the horizontal and vertical components of the velocity in projectile motion? Well, here we have a similar idea, the horizontal and vertical components of force. Which component of the force, the x component, the horizontal, or the y component, the vertical, do you think is helping to pull this object along? Pause the video and think about that for a moment. Okay, and you're back. I hope you can realize that it is in fact the horizontal component of force that is the one leading to the displacement here. The vertical component of force over here is actually kind of doing the same thing that this force is doing here, and that is nothing. It's contributing nothing to the work being done to move this object. Now, if you look at the angle theta here, you'll see that that's the same angle theta that I'm drawing in here. And if you look at F is along the hypotenuse, and Fx is along the adjacent side to theta here, so what we've got is Fx equals F times the cosine of theta. That just comes from SOHCAHTOA, choosing the cosine example. Cosine is adjacent over hypotenuse, so try that, and you're going to find this. Since Fx is the only force that we care about, what we have here is that the work done, which is equal to F times delta D, but only Fx, that's going to give us F cos theta delta D. And this is actually the formula that you will find in your book. So I'm finally going to highlight the formula that I want you to remember, that the work done is equal to F cos theta delta D. And you have to remember that when you are calculating work done, if a force is applied and there is a displacement, we also have to account for the angle between the force and the displacement. And so now, if you go back to this example here, you could look at it in a new way. You could think of the force as being directed up, but the displacement as being horizontal. These are at 90 degrees to one another. So in this formula down here, you would plug in 90 for theta. And what would you get? You would have the cosine of 90 degrees, which if you plug that into your calculator or if you remember it from math class, it's equal to 0. That's another reason to think of that no work is being done in this situation. All right? This, by the way, is the fact of the video, that the work is equal to F cos theta delta D. I want you to remember that formula and really remember what the theta stands for. Something really interesting happens when we understand the work formula. I've shown you a picture here of a racing car that has now deployed a parachute so that it can help it slow down. Now, let's analyze the forces that are at work here. If we just switch colors here so it's a little bit easier to see, the parachute provides a braking force, which of course would be a backward force like this to the direction of motion of the car. So F is backward, but the car, of course, is moving in a forward direction, even as it's being forced backwards. So here's the delta D. If you're being pushed backward, even as you move forward, this of course means you'll slow down. But what is the angle between a backward direction and a forward direction? Think about that for a moment, and I hope you can realize that the angle between these two vectors is 180 degrees. So if I knew how many newtons of force the parachute was exerting, and I knew the displacement, and if I plug those into the work formula, what would I get? I would go like this. W equals F cos theta delta D. And of course, I'd be putting in 180 degrees this time. What's the cosine of 180? If you remember from math class, the cosine of 180 is -1. In fact, the cosine of any angle that's greater than 90 but less than 270, so basically any backward slanting force, that's going to lead to a negative cosine value, which means you're going to get the idea of negative work. And so what exactly is negative work? Well, think about what's going on here. Negative work is being done on the car. And what is happening to the car? The car is slowing down. In other words, it's losing a certain kind of energy. What is that kind of energy? It would be kinetic energy. When the car slows down, it loses kinetic energy. The word loss in math often corresponds to a negative, and now you understand what's happening here. Negative work is being done to slow down the car. Now, what do you think would happen if instead of a parachute, we didn't have the parachute deployed, we just applied a forward force on the car, the same way this gentleman here is applying a forward force on some object, or the same way that someone is applying an upward force to move an object up, and so on. What would happen then? Well, one thing that would happen is the objects would speed up. Positive work is often related to an object speeding up, or in some cases it can be related to an object going up, lifting up, and therefore gaining what we call gravitational energy. So work is, if you will, an example of energy being transferred. Sometimes it's going into an object in one way or another, sometimes it's going out of an object. The cosine value will tell you whether the energy is going in or out. It's your job to figure out what kind of energy it is. Is it kinetic energy, like a car slowing down? Or maybe an object being sped up as it's pulled? Is it an example of something rising up higher, gaining gravitational energy because work is being done? As you try more and more examples, you'll get better and better at identifying exactly what's going on. And just to finish off, we're going to look at one more challenging example involving work. This one is best illustrated, or very well illustrated, by the concept of archery. If you've ever had the experience of shooting an arrow, then you know that at the beginning of pulling, right here, it's really easy to pull back on the bow. And when you get to the middle, it's a little bit harder. And by the time you get to the last few centimeters of pulling, it's really hard to pull. Of course, while you're doing this, you are exerting a force oops, which I'll try to draw in a straight line. There we go. You're exerting a force backward on the bow. And of course, you are displacing the bow backward as well. So it's not a surprise that when these two go together, this archer is doing work. Now, that means he is adding energy into this system that we call a bow and arrow. What kind of energy is he adding in? Let's go back to our list and see if we can figure it out. Now, it's not gravitational. He's not raising or lowering the arrow. Is it elastic? It is. A bow is an example of an elastic medium. It stretches and then it springs back to the original position. So by doing positive work, this guy is adding elastic energy into the bow. Of course, he can let go, and then that elastic energy will be released, and the arrow will gain kinetic energy in that transfer of energy that we discussed earlier. But the reason I'm showing you this example is not to talk about energy transformations again. It's to show you that sometimes when the force changes from a small number to a larger number and then to a very large number, you get a situation that is described by this graph here. This graph is also from your textbook, and it shows a situation where as displacement increases, so does force. Now, in this kind of situation, you can't use the formula F cos theta delta D for the simple reason that the force changes. It goes from a small number to a larger number. So if you were going to use this formula, what number would you plug in here? Would you plug in the smaller number? Well, then you'd be missing all of the work done at the higher numbers. You could put in an average value. That would be okay, but sometimes it's really hard to know the average value. So in that case, we go to this kind of graph, a force displacement or a force stretch graph. And as we've seen in previous graphs, sometimes you can just read the numbers off a graph and that gives you information you need. Other times we calculate the slope of a graph, and yet other times we calculate the area under a graph. Well, this is one of those times. The area under a force displacement graph equals the work done to displace some elastic object. And that would be what you would use if you had to calculate the work done by the archer. We could then calculate how much energy was stored in the bow, and therefore how much kinetic energy the arrow might get if we release it and let it start flying through the air. So there you have it. We've talked about a lot of different ideas relating to work and energy. We haven't done too much in the way of calculations. The calculations aren't too difficult here, so I'm going to leave that to you to try in the textbook. But as you're going to see in later topics or in later sections, we're going to get into calculating all the different kinds of energy, such as kinetic energy or gravitational energy. All right, that's it. Thanks for watching, and I'll see you guys in class. Take care.